Okay, hello class. I want to introduce you to a couple problems that we are going to return to specifically at the end of the class. You are going to work in teams and do final presentations about these projects. And these came from my research, and actually this is the National Security Agency. It's an unclassified version of a problem that was classified data. But when I had worked there for a summer, we had this, what we're going to call the NSA problem. And then this is from MIT Lincoln Labs. Their research group had this problem, again, affiliated with the project I worked on with them. And so we are going to ultimately, by the end of the semester, learn how to attack these, but I just want you to use these as a way to get to know each other, get to know your team members, how each of you think, and then have it as a starting point to see progress by the end of the semester. So okay, we're going to return to these a few times. So for now, what I want to do, I just want to introduce you to types of problems that we'll be able to solve in this class with optimization. And then I'm going to let you have a certain amount of time to just think about and see what are your thoughts at this point. Again, not thinking anyone can solve this. It's not the point. Okay, so the NSA problem, we had this graph, this network. This one shows undirected, but you could have directed. Undirected means you can go in either way along this link. You might have arrows. So if it was a directed graph, that's a further generalization or specific case of the problem. And so we have a network. And what we want to do is minimize the cost or the number of links that we're going to have to cut to do these things. So a lot of times in optimization, we are going to verbally describe the problem, objective, things you're trying to minimize or maximize. And then there's extra information that constrains you in some way. In this case, the constraints are that we actually want to maintain communication in this network between O and D. So a pair of nodes that live in the network. And then there's another pair of nodes that we want to cut the communication between, S and T in this case. So I need to know how many links do I have to cut that guarantee I can still get away from O to D, but there's no way that I can talk between S and T. Obviously, you can think about the applications and the reasons why the NSA wanted to do this. And this is an example network, but of course they would give you any network, hundreds of them. It doesn't look like this might be very easy to do by hand, trivial here. So whatever your algorithm is, it needs to also think about scaling up to other small cases that are much harder or much bigger cases. So it needs to be able to handle anything. And then there was also this other really interesting variant called the herding problem, where you wanted to herd all traffic through maybe a specific link like this. Maybe this red link now is something you could monitor. You could listen in on this if this is a phone network or something. And you wanted to make sure all traffic between O and D went through that link, but you still might want to cut the communication. So in this next assignment that I'm going to describe, you can pick either variant, the standard or the herding, to think about. Okay, now the MIT problem. This is a flight path planning problem. And we have some polygon. Here it's a square, but it could be any polygonal region. And there's some restricted no-fly zones that your plane cannot fly through. And then there's a target that you want to do something to. Let's think that this is maybe a relief mission. So we're dropping water or supplies. And we want to drop water or supplies at the target, but we want to minimize the time in these radars. And maybe these radars are only known, thinking back to some of our vocabulary, they could be known fixed or deterministically, stochastically, right? But let's assume the simpler case, we know that it exists here. Somehow we have information, and this radar centered here overlaps. So we want to come in and come out. So we want to minimize the cost of traveling to the radars because that's dangerous for us. We want to spend the least amount of time or no time if that's possible. Is that feasible for this problem? Yeah, it seems feasible that we can come through here without hitting radar. But there might be other ones where you're going to have to spend some time in some region and you want to minimize that. Obviously, constraint, you have to hit the target. Well, your plane also has some restrictions, some physical restrictions. You can't come like, right? Because you can't do that tight U-turn. So there's a turn radius that restricts how you're going to move. There is maybe a path length that you can't be if there's a lot of radars moving, weaving all over, because you might run out of fuel by the time you get to the other end. So there's some constraint there. And then they might give you a place on the boundary of this polygon that you enter and another one that you leave, or you might have to find that for. So ways to generalize the problem again. Okay, so we've just defined these again in terms of our objective function and our constraints. We have some language. And that's really it at this point, to have the language associated with this. And what I'm asking you is meet your teammates, just do some introductory chit chat. And then I want you to pick one of these two problems and spend 20 minutes, no more, discussing this problem. So what are ways you could attack it? What sorts of questions? You make a list of questions. What approach would you use? If someone was going to pay you $1 million, then you have to come out of this 20 minutes and have something, have some kind of answer, some ideas. What are you going to come up with? You guys have gotten very far in a math career, so you have to have some ideas. The other value of doing this is just learning how different people on your team think, and that's going to be really valuable going through the semester because we do a lot of group stuff. But there's a time limit, so again, you're going to do the best you can. Nothing that's written to be turned in, but I do want a 5-minute at the end. I want you, after you've chit-chatted, done your 20 minutes together as a team, brainstorm, come up with no more than 5 minutes, go to the Zoom, hit the record, and make a team presentation, 5 minutes or less, of what your results from that 20 minutes. So organize yourselves, make a few notes, things you want to say, again, questions you have, approaches you're going to try, extensions, things you think can work. Okay, 5 minutes for that. And that's what you're going to upload. So that's the result of this team attack. You'll be surprised at how many ideas you have and how far you can get. All right, have fun with that.